Hello everyone. We'll start on the first topic of this course, which is scalability of proof of work blockchains. So what is the scalability issue here? And you're familiar from the previous course that Bitcoin has very few transactions per second, something like 7 transactions per second. Right, so very few transactions get into the blockchain, and that's really not enough for a global, exchange system, a payment system. There's something like Visa would give you several thousands of transactions per second, and with what can you do with 7 transactions per second, right? It probably wouldn't be enough even for something maybe a little bit bigger than IIT or maybe POWChains or something like that, right? But certainly not for a global payment system, right? So of course things have moved on from beyond Bitcoin to Ethereum, and Ethereum might give you a little bit more than this, maybe of maybe like 15 or 20 transactions per second. But of the same order of magnitude as Bitcoin. So why is it only 7 transactions per second or 15 transactions per second for Ethereum? Right. So let's look at the Bitcoin blockchain. So we have one block coming every 10 minutes or so. Okay, so that on average a block is generated every 10 minutes, but it could take a little bit less or a little bit longer. And what is the block size? Well, Satoshi set it to roughly a maximum size of 1 megabyte. So if you try to fill up 1 megabyte every 10, with transactions, and that's the number of transactions you have every 10 minutes, then you end up with something like 7 transactions per second. So how could we increase this? Well, of course, you could increase the block size, right? Instead of 1 MB, maybe you make it 8 MB, right? Or let's say, even why not even have 100 MB, right? Or what you could try to do is, even if you keep it at 1 MB, you can try to reduce the spacing between blocks, right? Reduce it from 10 minutes. But there's a reason that Satoshi chose these numbers. Of course, initially I think he hadn't put any restriction on the block size, but he cleverly sort of slipped in the code when nobody was looking, right, in the early days. Okay, because he realized that if he announced publicly that he hadn't set a maximum block size, then somebody might have performed an attack and brought down the system, right? So without anybody knowing, he's updated the online code so that everybody just downloaded the latest update, and then Bitcoin from then on used only 1 MB blocks. Okay, but why did he set these values? So we might think, what happens, let's say, if you reduce this 10 minutes to, let's say, 1 minute? What's going to happen? So 10 minutes to, let's say, 1 minute. So what might happen is that you might have forks. So the blockchain might look like this. And even, let's say, if this one is chosen by most people, you might have forks and so on. Okay, so why does this happen? So we're not considering an attacker here at the moment. Let's say that all the miners are honest. So what happens is that the blocks take a certain amount of time to propagate in the network. So suppose these are the miners. Right, so let's say miner M1 has created a block, he sends it to M2. M2 has to validate the block. Okay, so he validates the block and then he forwards it because he's an honest miner. Honest miners are supposed to validate the blocks before forwarding. Right? So that's to reduce the work for other people, because some people might generate invalid blocks and you don't want to worry or bother the entire network to find out that it's an invalid block. So if a block sent by M1 is invalid, then M2 will just not forward it. Okay. So it takes a little bit of time for the block to propagate from M1 to M2. First of all, it goes across the internet. That takes some time. It's like transferring a 1 MB file, which takes some amount of time. After that, there has to be validation done by M2, and then it forwards the block and so on to M3. Right? So this takes some amount of time, and people have done some research about how long it takes to propagate throughout the network. So it may take of the order of, let's say, several tens of seconds. Let's say 10 seconds to a minute even. To propagate a block. Okay, so suppose we say that it takes 10 seconds, right? So because maybe the longest path in this network, in the peer-to-peer network, maybe let's say 3-4 hops, right? And so it has to propagate across the internet once, gets validated. That may take a few, let's say, tens of milliseconds and so on. And overall it might take 10 seconds for, let's say, most of the miners to get the block. Okay, maybe not everybody gets it. Somebody may be in a slow location, has a slow link to the internet. He may take longer to get the block. But let's say the people who control 95% of the hashing power in the network, let's say that they get a block within roughly 10 seconds or a little bit more than that. It might, in the worst case, go up to a minute. Okay. So if I reduce the generation time of blocks, instead of 10 minutes, I make it 1 minute, then it's quite possible that two people who are mining on the same block, they might generate blocks at roughly the same time, or before this person who's mining this block gets this one, he generates this one. Okay? So if you reduce this interarrival time from 10 minutes to something very small, comparable to this propagation time, you're likely to see lots of forks. Okay, so let's say this one was generated by M1 and this was generated by M4. So maybe this was generated a little bit before this one, but before M4 received this block from M1, he generated his own block. Okay, so you want to keep this large enough, and roughly what Satoshi is doing is he's keeping this interarrival time. So this is 600 seconds. He's keeping it roughly 60 times the propagation time of a block, right? So people say it takes about 10 seconds, right? That's what the research shows, and might be a little bit longer sometimes. Okay, so what's the problem with this sort of forking? Well, the problem is that you ideally want only a single ledger, right? A single ordered list of the transactions. This creates, first of all, multiple there are multiple blockchains. You want only a single chain. And which one is going to win? Right? It becomes an issue. Suppose we are in this sort of a situation. So somebody's transaction gets into this block, but maybe it's not in this block. So is that transaction going to end up in the final blockchain or not? So it creates uncertainty. You don't know whether your transaction is going to be there or not, right? I mean, if there was only a single chain being generated, then as soon as it gets in, you could be more or less sure, right, that the transaction is going to be there forever. Yeah, we are ignoring an attacker event. Suppose even if there is no attacker and you have forks, you have to worry whether the transaction is going to be there or not, because somebody might do a double spend and the transaction gets into this one, but there may be a double spend, let's say in some chain which gets added to this one, and this gets removed. Okay. So that is even if there is no attacker. But what if there is an attacker? So what does an attacker have to do to kill the longest chain here? So an attacker might have to generate a longer chain. So let's say the attacker wants to kill this chain, so he might privately mine a chain here, right? And now let's think, how long does he need this chain to be in order to kill this one? Okay, so let's see how many, let's say that these are all the attackers blocks and these are all honest blocks. So the honest people have generated 1, 2, 3, 4, 5, 6 blocks, but the longest chain is only 1, 2, 3, 4 blocks in length. Okay, so how many blocks does the attacker need to kill this chain? Well, actually 5 blocks are enough. Because the longest chain here is only 4 blocks long, right? 1, 2, 3, 4. Okay. So you see what has happened here. If all these 6 blocks which are generated by the honest nodes were in a single chain, then 5 blocks would not have been enough. The attacker would have had to generate, would have had to create a chain of length at least 7 blocks in order to kill that chain, which would have been 6 blocks in length. Okay. But now, because of the forking, the honest blocks are not all on a single chain. So these sort of are not part of the longest chain. These two are not part of the longest chain. So the attacker can generate a shorter chain of only 5 blocks in length and can kill that longest chain. So it's made this double spend attack actually easier for the attacker. He doesn't need to, let's say, put in as much effort. As let's say if all the blocks were in one chain, right? So maybe an attacker can get away with smaller hashing power, okay, for the same success probability of the double spend attack. Okay. So I'll just write that down. Double spend attacks are easier now. So by easier, I mean for the same success probability, he would have, he could get away with a smaller hashing power, right? So maybe for, let's say, probability of success 10 to the power of -3, let's say in a standard double spend attack, he would have needed, let's say, 10% of the hashing power, but now maybe with just 8% or 6% of the hashing power he might get away. Right? So in general, forking is bad, which is why Satoshi set this time to be 10 minutes. Right? So what about if I increase the block size? Okay, so this is one idea. What if I make 1 MB, let's say 8 MB? So it seems, why don't we do this instead of reducing the interarrival time between blocks? Right? So what could go wrong over here if I make this 1 MB block 10 MB? And in fact, this was a proposal in Bitcoin, and there was a big fight among the miners, right, whether to adopt that chain, that particular change to the protocol. And most of the miners, in fact, rejected that. Okay, and few people like Gavin Anderson, who was one of the first people in the Bitcoin group of people, he was there at Satoshi's time too. He wanted to increase the block size, but most of the other people sort of rejected his idea. So why is that? Well, one thing is that the propagation time is going to increase because this validation time goes up. Let's say that this is proportional to the block size, right? Because if there are more transactions in the block, it takes more time to validate. Okay, and network delays will also go up based on the block size. And why is that? Well, because it's like transferring a larger file, right? So instead of sending a 1 MB file, you're sending an 8 MB file. So it's just going to take longer for that file to get across. Okay. So block propagation time is also going to go up. Okay, the validation time is going to go up. So the end-to-end delay, instead of 10 seconds, this may end up being a minute or 8 minutes. Right? If you increase the block size, I beg your pardon, it might go up to 80 seconds, let's say, if you increase the block size from 1 MB to 8 MB. And again, you would have the same problem of forking, right, which will create easier attacks and so on, and uncertainty in the blockchain and so on. Right? So there's another issue, sort of unrelated to what we discussed till now, is that 8 MB means you have more transactions in the blockchain, right? So there's another problem. So first of all, there is forking. Due to larger propagation time. But the other problem is that you have blockchain size goes up faster. The problem with a larger block size for the same number of blocks means that the number of UTXOs may go up. And typically you want to keep a lot of this UTXO information, you want to keep it in memory, and that could be an issue. Right? So you may end up, so why do you want to keep this in memory? Well, because when you get a block, you have to validate it, and if you have all the UTXO information in the memory, you can validate the block faster. Okay, so people, let's say smaller miners who don't want to spend too much on having huge amounts of memory, they would be at a disadvantage, right? Because maybe they would have to have some UTXOs, let's say on disk, and it would take them longer time to validate. Whereas for powerful miners, let's say very rich miners, maybe they can have powerful machines with large memory and they'll be able to validate blocks faster. And that gives them an advantage. Right? Okay, so this is in memory, which implies you want larger memories. Okay, so this is one of another reason, I should say, while lots of miners actually oppose this proposal to increase the block size to 8 MB. Okay, so there was actually a hard fork with some subset of miners adopting the change of an 8 MB block and most of them sticking to a 1 MB block. Okay. So this happened about 2016-2017 time frame. Okay. Anyway, so Bitcoin till today has hardly 1 MB block sizes. Okay, and it's slightly You can have slightly larger blocks because of something called SegWit. Okay, but for our purposes, let's just assume that it's a 1 MB block with 10-minute intervals between blocks. Okay, so there are very few forks which happen in the Bitcoin blockchain. So this is one reason why you keep the blocks small and the transaction rate is slower. Okay, so let's move on a little bit and think about Ethereum, how this actually affects Ethereum. So in Ethereum too, you have blocks and there's proof of work just like in Bitcoin. So they decrease the inter-arrival time to hardly 15 seconds. So it's much smaller, but of course they don't have 1 MB blocks, they have much smaller block sizes. But anyway, because of this 15 seconds, they do have a lot of forking. Right? So this creates an issue, right? I mean, of course, they want to live with this sort of a system. So they don't follow exactly the longest chain protocol. They adopt something called Ghost. So Ghost is a little bit different. It can live with some amounts of forks in order to reduce the chances of this double spend attack which I talked about here. So notice here what I said in this particular graph. We said that there are 6 blocks generated by the honest miners, but the longest chain is only 4 in length, right? And so the attacker had to generate a chain of 5 blocks just to kill this longest chain. So what the proposers of Ghost said, they said let's not look at the longest chain. Let's look at let's weight the chain a bit differently. So they said that I will find my preferred chain by starting from this block, starting from the root. Let's say this is the genesis block. And let's maybe draw this same chain here. So let's look at this, and let's say that we had attacker generating a chain here. Yeah, this 1, 2, 3, 4. Let's say that we had something like this, similar to the figure we had earlier. So with the Satoshi's rule, this particular attacker's chain can actually kill the longest chain over here. Okay. So what do we do in Ghost? So Ghost says, let's weight this chain a little bit differently. So let's say that the attacker makes his chain public. Okay, so we are going to count these blocks as well. So what Ghost says is that you weight a particular block, you give it a number, let's say depending on how large its subtree is. Okay, so let's forget about whether the target changes and so on, those complications. Let's say that the same amount of proof of work has to be done to create each of these blocks. So what is the weight of this block? Well, it's the weight of the full tree of which it is the root. So we're going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay. And what is the weight of this one? This is going to be 12. What is the weight of this one? Well, it's 1, 2, 3, 4, 5, 6. And what is the weight of this one? Well, it's 1, 2, 3, 4, 5. So when you want to find the sort of the valid chain in this particular tree, what Ghost says is that you start from the genesis block and you follow the heaviest block after that. So what are we going to do? So we're going to start here and we reach here. There is no fork, so we don't have to worry. But now we go according to this, right? Because this block has less weight than this one. Okay, and so what is the weight of this? Well, it's 4. This is 3, and each of these is 1, right? So the longest chain goes this way, and of course there is some ambiguity over here, right? Either of these would give a equally long chain. But what we've ended up doing is that we've ended up sort of making the attack harder. Okay, for the Satoshi's rule, this chain is going to kill the longest chain here, but not if you're using Ghost, right? So the Ethereum people said that we will live with some amount of forking, but we will use Ghost, right? Okay, so that was one thing, but of course maybe for this particular attack it's better, you know, but maybe there are other attacks for which maybe there may not be an advantage. But anyway, whatever it is, it's a slight change from Satoshi's rule. Okay. So what else does Ethereum do besides this? So Ethereum has smart contracts. So it's going away from the UTXO model of Satoshi. So each transaction can be viewed as just a piece of code. And the code can even have for loops. So these for loops were not allowed for Bitcoin. Okay. Right? So there was there's this big argument which goes on that is Bitcoin's language Turing complete or not, and one student had brought it up in the last course, and of course a lot of papers say it is not Turing complete, right? But some people go to great lengths to say that it is Turing complete, right? But let's think about it as a high level, that for loops are not allowed in Bitcoin, whereas you can have something like a for loop or a while loop in Ethereum. Okay, so maybe you could run a program. You can sort of have a very elaborate program with the Bitcoin language, which is sort of Turing complete, maybe, right? With the giving, if you look at the actual technical definition of Turing completeness, but the difference is that here with a small piece of code, let's say with 5 lines, you can have something running forever. If you have let's say a for loop which runs, let's say, millions of times, right? So even a 5-line code could be running for a very, very long period of time, right? But with 5 lines of Bitcoin, you would not be able to do that because of the the language that is used over there, right? Maybe you could have an equivalent piece of code in Bitcoin, but that particular transaction would have to be very large, maybe thousands of lines, in order to do the same work which, let's say, a small transaction is doing in Ethereum because of this for loop. Okay? So this creates a problem, and that is that even a small piece of code could keep miners busy forever. Okay, you could have a transaction which is computationally intensive. And this is a term that I will use quite often. So what do I mean by this? A computationally intensive transaction is a small piece of code which runs, let's say, for a long time. Okay, so just to execute this transaction, it could take, you might have to run millions of instructions, okay, instead of just 5 instructions or something like that, which might have been for Bitcoin. So how do we deal with this? Because if you recall that every miner, we said, has to validate a block before actually forwarding it to the next miner. And even if the block is small, let's say 1 MB or something even smaller than that, it could take him, let's say, minutes just to validate that block, right? Because you can have a for loop which runs, let's say, millions or billions of iterations. So that's another problem. So now we have a different problem, that you even may have a small block and the interval time could be whatever, 15 seconds, or even if it's 10 minutes, right? Just just executing the transaction, that block will take a long time, so the propagation delay of the block will go up, right? And so even if the blocks are generated every 15 seconds, you might have large number of forks just because it takes long for the block to propagate in the network. Okay. So I generate a small block, let's say in Ethereum using M1, M1 sends it to M2, but it has computationally intensive transactions, so it takes very long to validate the block, right? And so the propagation delay goes on. So this is again a problem, and as we look at this problem in some more detail a little bit later on, but how do we deal with it? So what Buterin and others did for Ethereum is that they have the concept of gas. So you're probably familiar with this from the last assignment of the previous course. But essentially what the gas is going to do is it's going to limit the computation for a particular block. So gas is related to the amount of computation. So what Ethereum does is it has a list of transactions, list of instructions, I should say. So let's say you have an add, multiply, and so on, right? Right, an assignment. And there is a gas related to this, and maybe the addition, let's say, costs 2, and a multiplication might cost, let's say, 5, and the assignment might cost 1, and so on, right? Okay. So what you have to do is that first of all, you have a maximum gas limit for a block. So this means that whatever you put in that block, whatever transactions it has, it better not consume more than this amount of gas, right? And roughly the gas would be proportional to how many, let's say, how much time it takes, let's say, to run any one of these instructions in the Ethereum virtual machine. Okay? So there's a limit on the gas, and any block which sort of runs for longer than that gas limit, okay, so you can count, let's say there are a certain number of adds, or a certain number of multiplications and so on, while you execute all the transactions in a block. All of them should not consume more than this total amount or the limit of a gas for a block, right? So let's say that you have a transaction, this is a block, this This is transaction 1, 2 and so on. So the total gas should be less than your gas limit. So there are certain rules for setting this gas limit which are built into the Ethereum protocol. Okay? And of course you would want to maybe change it over time for some reason. Let's say that you have more powerful machines getting built every day, right? As you know, Moore's law and so on keeps, let's say, continuing. You might want to increase that gas limit over time. Okay, so there are various rules. But let's for the moment assume that the gas limit is fixed, right? That any particular block, let's say you don't want it to run for, you don't want an EVM to take more than, let's say, a few tens of milliseconds to execute this block, right? So you set the gas limit appropriately. So how is this total gas limit going to be distributed among these transactions? So what we do over here, so each transaction should say what is the maximum gas for that particular transaction. So it specifies the maximum gas to run it. Okay, so you might have a for loop or whatever, but you better specify how much gas it's going to take, right? And obviously that gas for that transaction shouldn't be more than the gas limit of a block, obviously, because otherwise you cannot put it in the block if it actually takes that much gas to run. Okay. So what you have here, so suppose we have a for loop, right? So let's say I put the maximum gas over here, okay? And now so how is this going to help? Well, of course, anybody who's, let's say, creating a block like this might want to look at these maximum gases for each of these transactions and put in transactions so that the sum of these is less than the gas limit of the block, right? But there are other issues too. So what sort of transaction fee to pay for a transaction? So this was something we didn't discuss so much for Bitcoin. We just said that if A pays B, then he leaves a little bit, right? The input is a little bit greater than the output, and that is sort of the transaction fee. Right? We didn't look at complicated code where you may have, you know, for loops, or because you don't even have for loops in Bitcoin, but you can have something more complicated than A paying B in Bitcoin, right? But over here, even if you have a small piece of code, I mean, you could have this transaction running for a long period of time, right? And so what transaction fee should you put in? So normally you would expect the transaction fee to be proportional to the time it takes to run this transaction, right? So you want the transaction fee to be proportional to the time spent, let's say that the execution time. Which is roughly equal to the gas spent while actually running this transaction. Okay, so this is the maximum limit. So the person who's creating this transaction says, I'm guaranteeing that it's not going to be greater than this limit, right? And so the actual gas is going to be a little bit less than this, right? So maybe the maximum gas, let's say, is 100 units. But the time taken to actually run it may be a little bit less, right? Because maybe each loop, let's say, is 10 units, and this person estimated that in the worst case you would need 10 loops, right? But maybe only it was run 8 times, because of which 80 units were actually used. Okay, so this particular miner should be, this particular person who's creating the transaction should be willing to pay a transaction fee, but equal to this particular gas, right? So the question is, what should he set, right? So if there's a rich guy, let's say Bill Gates is generating this transaction, even if it's 80 units, he may be willing to pay $1 million for whatever reason, right? Whereas let's say you and I, who might generate a similar transaction which uses up only 80 units, but we can't pay $1 million, right? We want to pay a smaller amount, right? But Bill Gates may want to have an advantage over us about getting his transaction in, right? And the way he would do it is he would pay a higher transaction fee, just like in Bitcoin, right? Somebody who pays a higher transaction fee, his transaction might get in sooner into the blockchain. So how do you change that? Well, you have a gas price which is also specified here. In addition to this, you would put the gas price also mentioned in the transaction. So this is the, let's say, the Ethereum per gas unit that the person who's generating the transaction is willing to pay. Okay. So maybe you and I created another transaction which had the same 100 units as the maximum gas, right? But Bill Gates created this one, so he puts a higher gas price compared to us, right? So that his transaction has a higher chance of getting into the blockchain, right? Right. So okay, so his transaction gets in, but there has to be a way of making him pay that amount, right? So what would be done over here is that Bill Gates would have to deposit an amount equal to gas price times the maximum gas that he estimates for his transaction. So you deposit in the transaction an amount equal to gas price multiplied by maximum gas for the transaction. So this has to be deposited, right? And what you do is that maybe he needs to deposit the full amount, right, corresponding to this maximum, but only 80 units were actually executed. So it seems to be a bit unfair to actually take all that amount, right? Because it's possible that the person creating the transaction doesn't know exactly how much it's going to cost. Right? Because maybe there are some inputs over here which are not determined, right, beforehand. Maybe it depends on the transactions which get into the block just before his, right? In which case, maybe it takes, instead of 80, it might have taken 30 units, or it may have taken 90, right? So his estimate was 100 in the worst case, but he doesn't know exactly, right? So it's a bit unfair to take all this amount and give it to the miners, especially because if the miners have to execute this transaction for fewer gas units. So what you do is you refund him for the gas which is unused. Okay, and so here this unused gas we are going to say is 100 minus 80, right, which is 20 units. Okay. and it may be more too. Let's say if there was only 30 used, then the unused gas would have been 70 and he would have got a refund for this. Okay. So that's all done once this transaction is executed, right? So only the amount corresponding to the gas used by the miners, okay, while executing this is confiscated by them as, I shouldn't say confiscated, but is taken by them as transaction fee. Okay, so transaction fee is the difference between these. Okay, so this is at a high level what Ethereum does, right? So each person who's generating a transaction has to estimate how much gas his transaction is going to use. He has to also propose a price, and he will sort of propose something roughly to, depending on what other people are proposing in the recent blocks, and he has to deposit an amount equal to this, assuming that the maximum gas is used in the transaction, and he gets a refund for the unused gas. So Ethereum is a little bit more complicated than Bitcoin because you have things like for loops which are allowed, right? What happens, let's say that if the gas required for the transaction actually exceeds the maximum gas proposed by the person generating the transaction. Okay, so that might happen. So somebody creates a transaction, he says 100 units, but this for loop may actually run for very long and it may exceed 100. So then what happens? So that's hopefully a rare case, but it can happen because somebody didn't estimate the maximum gas well enough. So in that case, what should we do? Because he hasn't deposited enough money to pay for his gas, right? So what do we do? Should we execute his transaction and stop as soon as 100 units are over? But then maybe the for loop hasn't completed even. Maybe you're in between, right? So that's an issue because this person expects his transaction to be completely executed. So what Ethereum does is that the miners will execute his transaction completely. I mean, not completely, they will execute it till 100 units of gas have been used up, and they find that the transaction hasn't ended. So what they do is they confiscate this full amount which he has deposited, this amount, the gas price multiplied by whatever the maximum gas is. So the full deposit is confiscated, and the state is rolled back. The state of the virtual machine is rolled back to the point it was at the beginning of the transaction. So it is as if the transaction wasn't executed at all, except for the part of the transaction where his deposit is sort of confiscated by everyone. Okay, so let me write that down. So first of all, let's talk about what is the state of EVM. So the details you can find in something called the yellow paper. On Ethereum. Okay, so you have, let's say, a lot of variables, right? Every time somebody creates a smart contract, let's say that these belong to the smart contract 1. This is the smart contract 2 and so on. These are the variables corresponding to various smart contracts, right? And every time create a particular smart contract, let's say somebody creates a smart contract, let's say new variables have to be created in the EVM, the Ethereum virtual machine. Right? So a transaction can create a smart contract okay, so this could just be the code, right? You have various functions in the smart contract, let's say. So the code is created in a transaction, but it can also execute smart contracts. Okay. So maybe a smart contract has been created, and another transaction is just saying run function 1 of this smart contract, run let's say function 5 of another smart contract or whatever, right? Okay, so anyway, when you create the smart contract, certain some amount of memory has to be allocated for all the variables of a particular smart contract, right? And Ethereum has something called a trie, in which all these are organized. Okay, so I'll just draw it this way. This is the trie. And finally you have a hash which is going to be representative of all these variables. So the entire state, I will call the values of all these variables at any particular point in time as the state. Let's say the state is the values of all variables, let's say. Okay. And it may include more than this, plus let's say any other things, right? Code, etc. Right? Whatever is representative of the full Ethereum virtual machine, that is captured by this single hash, right, of all this data. Right? And of course, this is made efficient in a way that suppose the variables of this smart contract are updated but not these, then in order to calculate the hash, you don't actually have to go through all these variables. Right? Just like a Merkle tree is quite efficient. If you update one leaf of the Merkle tree, you only have to update the hashes along the path to the root. Right? So something similar is done over here, right? And you can efficiently update this hash if only, let's say, a few values are updated. Right? So this, let's say this hash is the state of the EVM. So let's go back to what we were discussing earlier. So let's say you have a particular transaction in a particular block. Let's say that these are all the transactions in a block. So let's say that this is the state over here, this is the value of that hash, and you keep executing these transactions one after the other, and the state gets updated. Let's say I'm going to call this S1 and this is S2 and so on. Right? So if a transaction doesn't have enough gas, what I'm going to do is I'm going to roll back. So what we do is, let's say you said 100 units of gas. I executed this transaction up to 100 units, but the transaction wasn't over. I was still stuck in the for loop. So whatever state I'm currently in over here, so what I'm going to do is I'm going to cancel this and go back to S1. So this is the rollback. To the previous state. and I confiscate the deposit. Okay, so the state might change a little bit because here the deposit wasn't confiscated, but here you're going to do that, right? So because of confiscation, let's say it becomes S1 dash, right? Not very different from, I mean, the variables, if you look at them, are not very different from what they were after transaction 1 was executed. Okay, but slightly they get modified when this amount is confiscated from the person who generated this transaction, and it goes to the miner who includes this transaction in his block. Right? So this is what Ethereum does, and it ensures that first of all, that the total maximum gas of all these transactions is, the sum of those is less than the gas limit, and you can see that in fact when you execute a particular block, the gas used is going to be less than the gas limit of the block, right? Because even if a transaction takes longer than the amount, that the maximum amount specified, you just terminate that transaction, roll back the state, and confiscate the deposit. Right, so this is how Ethereum works, and you can see it's much more complicated than Bitcoin, but you can also do things which are more interesting. Pretty much what any program can do, let's say any C program can do, or Python program can do, you will be able to do, let's say, with Ethereum, right? Because you can have for loops and things like that. Okay? So you can have more interesting smart contracts than you could have with Bitcoin. Right? But the more complicated your protocol and your code and so on gets, the more attacks also might be possible. So you have to be worried about that. Okay?